Alright, so NASA just saw something in the latest data from this interstellar visitor, 3, i.e. Atlas. And honestly, it's making it really clear that this object is nowhere near done with whatever it's going through right now. I know a lot of people were kind of hoping that by this point in the story, things would be straightforward, like, okay, it flared up, it survived its close pass by the sun, and now it's just quietly fading away into the distance. That would be nice and simple, but the update that came through today, it's telling us that's absolutely not what's happening here. 3i8 Atlas is still changing. It's still evolving. And if you've been following along with me on this journey, watching this thing from another star system pass through our little corner of the universe, you really don't want to miss what happens next. Because what NASA picked up in today's observations might actually be the strongest sign yet that this comet isn't at the end of its transformation. It's right in the middle of it, and we have no idea which way it's going to go from here. So, let me walk you through what they just saw, because it's honestly pretty wild. Before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming next. Today's observations weren't really supposed to be dramatic. It was just another routine, coordinated run. You've got ground-based telescopes, a couple of deep space cameras, all pointed at this thing at roughly the same time. They're just building another slice of data for the timeline. Right, standard procedure. You take the images, you stack them, you compare them to what you saw yesterday and the day before. Pretty normal stuff at this point in the mission. But when the teams actually lined up, yesterday's stack against today's stack, when they really looked at what was happening in that inner coma, the glowing cloud of gas and dust right around the nucleus, they saw something very different from what they expected. In yesterday's images, the glow around the nucleus looked relatively familiar for this comet. It was elongated, a little bit twisted, sure, but it was still dominated by one main axis of brightness, basically one big bar of light feeding into the tail. You could look at it and go, okay, that makes sense. That's how this thing has been looking for a while now. But in today's stacked frame, that bar is just gone, completely gone. Instead, what they're seeing now is that the inner coma has developed this layered, almost shell-like structure. And I need to emphasize, this isn't like those clean, neat donut shapes we saw earlier in the encounter when it was closer to the sun. This is different. This time, it looks like a series of overlapping arcs, like someone took a pencil and drew these faint, curved ribs right through the inner glow around the nucleus. One arc is tight and bright, sitting really close to the core. Another one is fainter and sits a little bit farther out. And then there's a third one, barely visible, stretching even farther out into the coma. And it's tilted at a slightly different angle from the other two. And that right there, that's your first big clue that 3i Atlas is still actively evolving. Those arcs aren't random. They're not just some quirk of how we're looking at it or some artifact in the image processing. They're actually snapshots of past activity. They're waves of material that got thrown out from the nucleus in separate bursts at different times. And now they're frozen in place as these expanding shells moving outward through space. The fact that a new inner arc has appeared since the last literally yesterday, means that something inside this comet has changed again. And it changed recently enough that we can still see the footprint of that change happening in real time. Think about that for a second. This isn't ancient history. This is happening now. Something shifted inside this nucleus within the last day or so, and it threw out a fresh wave of material that we can now see as this new bright arc. Then there's the light curve, and this is where things get even more interesting. The light curve is basically just tracking how bright the comet is over time as it rotates. And yesterday's brightness pattern, when they measured it over one full rotation, already looked complicated. It wasn't a simple, smooth curve. There were more than one peak. There were slight shifts in timing, and there were hints that multiple active regions on the surface were kind of competing for control, each one contributing to the overall brightness as the comet spun around. But today, when NASA's team took the new photometry data, the new brightness measurements, and folded it over the previous rotation period to see how things lined up, two things immediately jumped out at them. First, the rotation period itself has nudged again. It's a tiny change, just a slight shortening of the period. But it's enough that the main brightness peak now arrives earlier than it should if the spin were completely fixed and stable. The comet is spinning just a little bit faster than it was before. Second, those smaller secondary peaks in the brightness curve have merged together into this more complex plateau. Instead of having distinct, separate peaks, they're now overlapping each other, creating this more complicated pattern. So, instead of seeing a nice, simple rhythm like bright, then dim, then bright, then dim, the comet now has this more jagged, irregular pulse. It's almost like it's running on 2 or 3 different beats at the same time, instead of just one steady rhythm, and that pattern is exactly what you would expect to see when two things are happening simultaneously. First, the spin state of the comet is still changing. It's not locked in yet. And second, new vents are opening up and joining the activity. while older vents are starting to fade away. In other words, the comet's rotation and its activity pattern are still evolving together, hand in hand. One affects the other, and they're both still shifting. Now add the spectra into the mix, and the picture gets even more complete. Spectra are basically measurements of the specific wavelengths of light coming from the gas around the comet, and they tell you what kinds of molecules are out there in the Comet dot and the new spectral measurements from today's show, a subtle but really important shift in the balance of different chemical species around 3E Atlas. Some of the lighter, more volatile components, the stuff that evaporates, really is the stuff that dominated the spectrum when the comet was closer to its closest approach to the sun. That stuff is starting to fade now. At the same time, the signatures associated with deeper, more refractory isos, the stuff that's harder to evaporate, and larger dust grains, those are becoming relatively stronger in the spectrum. What that means is the outer coma is starting to look older. It's getting dominated by processed dust that's just drifting away from the nucleus. But the inner region, right near the core, is getting enriched with fresh material that wasn't there a week ago, brand new stuff that's just now being exposed and released. And that's exactly the pattern you would expect to see if the heat wave from the comet's closest approach to the sun is still migrating inward through the nucleus, slowly working its way deeper into the interior, turning on layers that have never been exposed to sunlight before, layers that have never vented before in this comet's entire existence. So, when you put all of that together, when you look at the complete picture, what do you have? You've got new inner arcs appearing in the coma structure. You've got a rotation period that's getting slightly faster and more complex. You've got a gas and dust mixture that keeps tilting toward deeper, previously hidden material that's only now being activated. 3. Atlas isn't just cooling off and settling down after its close encounter with the sun. That's not what's happening here at all. It's peeling layer by layer. It's peeling. And here's the thing that makes this really significant. Each layer that becomes active doesn't just add more of the same behavior. It doesn't just make the comet a little bit brighter or add a little bit more to the tail. It actually changes the behavior entirely. New fractures open up in the surface. New jets start firing from new locations that weren't active before. The balance between gas and dust shifts, and that changes how the entire coma looks visually and how efficiently sunlight can push on the material, creating what we call radiation pressure. And that brings us to the dynamics, the orbital mechanics, which is where this gets really important for understanding what might happen next. When NASA's orbit determination teams ran today's astrometry measurements through their trajectory solver, when they tried to figure out exactly where this comet is and where it's going, they were really hoping that the non-gravitational force would finally start to taper off in a clean, predictable way. The non-gravitational force is basically that tiny rocket engine effect from the jets. When gas vents off the surface of a comet, it doesn't just make the comet look brighter. It actually pushes on the nucleus like a tiny thruster, and that affects the orbit in ways that pure gravity can't explain. You have to account for it separately, and the hope was that by now that force would be settling down, becoming weaker and more predictable as the comet moves away from the sun and activity naturally decreases. But instead, the magnitude of that force has held nearly steady. It hasn't dropped off the way they expected. The direction of the force didn't swing around as violently as it did on some earlier days, which is good, but it still had to be adjusted, still had to be nudged in their models to make the data fit properly. And the message from those numbers is actually pretty simple and pretty clear. 3 Atlas is still actively steering itself through space. It's not as chaotic as it was at peak activity, but it's still enough that you absolutely cannot treat this thing as just a passive rock falling through the sun's gravitational field. It's more complicated than that. Inside this nucleus, vents are still switching on and off. Torque is still being applied to the body, changing how it spins. The spin itself is still being adjusted by the comet's own outgassing, by its own internal activity. And this is where the word evolving stops being just a neutral description and starts becoming something more like a warning. Because think about it this way. A stable comet, a normal comet, might flare up when it gets close to the sun. Sure, but then it settles into a quiet, predictable fade as it moves back out into the cold outer solar system. You can model it, you can predict what it's going to do, and you can basically check the box and say, okay, we understand this object. But an evolving comet, especially one that came from another star system, one with an internal structure and composition that we know absolutely nothing about from any prior experience. An evolving comet is under constant reconfiguration. It's not in a stable state. Things are still changing. Every time a new vent opens up, it changes the stress map inside the nucleus. Forces get redistributed. Weak points that were under compression might suddenly be under tension, or vice versa. Every small spin-up, every time the rotation rate increases even a little bit, that changes how centrifugal force pulls on weak regions in the structure. It's like spinning something faster and faster until the forces start to overcome the strength of the material. Every fresh layer of activity, every time a new deeper layer gets turned on and starts venting. That adds strain to a body that's already been stretched and stressed by months and months of heating and cooling cycles, expansion, and contraction as it made its way through the inner solar system. So, here's where we are right now. We're not at the point where we can confidently say this thing is breaking up. We can't say that yet. The data doesn't support making that claim right now. But the picture that's emerging from today's data, from all of these separate lines of evidence pointing in the same direction, is this. 3 Atlas is still in transition. It's not in its final state. It hasn't settled down yet, but it's also not in its initial state anymore, not in the configuration it arrived in. It's somewhere in the middle of an internal rearrangement, a transformation that was triggered by its one and only close pass through our solar system. And from here, there are basically 2 ways this can go. If, over the next few days, those arcs we're seeing in the coma smooth out and become less distinct, if the rotation period stabilizes and stops drifting around, if the non-gravitational force from the jets finally starts to drop off cleanly and predictably, then we might be watching this comet slide into its final, quieter configuration. It would be scarred, definitely altered by the experience, but fundamentally intact. It would survive, and eventually, it would just drift back out of our solar system and head back into interstellar space, carrying the marks of its visit with it. But if, instead, over the next few observations we see new shells appearing in the inner coma, if the spin drift continues and the rotation keeps changing, if the jets keep switching direction and the activity pattern keeps getting more complex instead of simpler, then this phase we're in right now, this evolving phase might be the last stable phase before something more dramatic happens. We might be watching the prelude to a breakup event. We might be seeing the early warning signs of a nucleus that's being stressed beyond what it can handle, beyond what its structural strength can sustain. In either way, no matter which direction this goes, we're living through something genuinely unique here. This is not a routine observation campaign. This is not just checking boxes on a mission plan. We're not just taking a single snapshot of an interstellar comet, writing up a paper, and filing it away in the archives. We're watching it change. We're watching it evolve. And we're watching it happen again and again in real time, with new data coming in every single day showing us something different from the day before. There's never been anything quite like this. We've never had this kind of continuous, high-resolution view of an interstellar visitor going through this kind of transformation. The first interstellar object we detected was already on its way out when we spotted it. We got a few glimpses, and it was gone. Borisov, the second one, was more comet-like, and we got better observations. But it was relatively stable, relatively well-behaved. It didn't do this. But 3 Atlas is giving us a front-row seat to something we've never seen before. An object from another stellar system with a completely unknown history, with a composition and structure that formed under conditions we can only guess at, going through the crucible of a close solar pass and being fundamentally changed by the experience, and we get to watch it happen day by day, observation by observation. We get to see how it responds, how it changes, how it either adapts and survives or reaches a breaking point. That's what makes this so compelling. That's why every new data release matters, because we genuinely don't know what's going to happen next. We can make educated guesses. We can build models. We can look at what happened to other comets in the past. But ultimately, this is uncharted territory. So, if you want to see how this story ends, if you want to find out whether 3 Atlas manages to finish this evolution without tearing itself apart, you need to stay tuned. Keep watching, keep following along, because the next observation could be the one that tips the scales one way or the other. This thing is still writing its own story, and we're just here to read it as it unfolds, one page at a time.